Okay, welcome. So today we are going to talk about combinations with repetitions. So here's a typical problem. We are given a box which contains let's assume a very large number of balls in each of 4 colors, so which are red, blue, green and yellow. Now the question is, find the number of ways in which one can choose 10 balls from this box. Okay. So for instance, let us see what are various examples of choices. So let us just look at a few examples. So how would we encode a choice? We could keep track of the number of red balls, blue balls, green balls and yellow balls. So for instance, one choice could be, maybe we pick 3 red, 3 blue, 3 green and 1 yellow. Maybe we choose 5 red. So here's one possibility. Here's another choice. You could pick 5 red, 1 blue, say 2 each of green and yellow, okay, and so on. So you could imagine various such choices of some number of red, some other number of blue, green and yellow, but of course the total number of balls that you pick has to be 10. That's of course the key constraint. So observe that this is different from the problem of combinations that we have looked at so far, because the typical problem of combinations says something like you have got n distinct objects and from those n objects you want to choose r of them. So recall that the other combinations problem, the typical combinations problem that we have looked at so far, for which the number of choices is n c r, is the number of ways of choosing r objects from n distinct objects. So this is number of ways of choosing r out of n, keyword here being distinct, objects. Now combination with repetition just means that we don't really have distinct objects anymore. For instance, here what we have is, let us say we are given a very large number, let us say 100 each of red balls, blue balls, green balls and yellow balls, and from amongst these say 400 balls you need to pick 10 of them, but the thing here is the original objects are not distinct anymore. Many of them are alike. For instance, the 100 red balls are all alike, the 100 green balls are all alike and so on. So the key distinction really comes about in the assumption that the initial set of objects is distinct. So this is the usual combinations problem. Now what we are looking at is what you would call combinations with repetitions. So observe that this sort of encoding here, the number of red, blue, green and yellow balls. So let us say the most general encoding is, let us say there are x red balls, y blue balls, z green balls and let us say w yellow balls. Then what this is saying is, what are all the number of choices for non-negative integers x, y, z and w such that their sum is 10. So observe here that it is not necessary to choose a ball of a given color. For example, another choice here could be, I could choose red, blue, green, yellow. You may choose 0 red balls, 0 green balls and maybe 5 each of blue and yellow. This is also a valid choice. So you are not required to choose 1 ball of each color at least. You can choose 0 balls for instance. So here is another equivalent reformulation. So here is problem 2, which is really the same as problem 1 in some sense. Find the number of solutions to the equation, number of solutions of the following equation, x plus y plus z plus w equals 10, with the constraint, with the requirement that x, y, z and w be non-negative integers. So let us just say this where x, y, z, w are non-negative integers. Okay, so these two problems are really equivalent to each other. Okay, so now so let us look at the typical method of solution. It requires a slightly different way of thinking rather than the usual combinations problem. So how do we solve this problem? So here's the typical solution. How do you find the number of such solutions to this equation? So let's encode it in the following way. So what we need is, so let's think about it in the formulation of problem 2. What we want is the following. Let me write down 3, 4, 5, 6, 7, 8, 9, 10. There are 10 ones now on the board. Okay. Now what we will do is the following. If you are given a solution x, y, z, w, for instance, suppose I have x equals, so let us take the solution that we already had. For instance, if you take x equals 5, y equals 1, z equals 2 and w equals 2. So 5, 1, 2, 2, we will think of it as follows. So x is 5. So let me see, there are 5 ones, this much is x, y was 1, so that is y, z is 2 and w is a 2. Okay, so we first mark these off in the list of ones, and then we do the following. We sort of draw dividers between them. So here's a divider that I have drawn in red which separates the x from the y. Now there's, once I move to z, I put another divider, and between z and w I have yet another divider. Okay. So what I have done is written a string of 10 ones with 3 dividers, in between. Now this entire picture here represents the solution x equals 5, y equals 1, z equals 2 and w equals 2. So this picture here represents the solution 5, 1, 2, 2. Okay. And let us sort of look at a few more examples. So let me take the next one, 3, 3, 3, 1 for instance. So here's the solution 3, 3, 3, 1 would be represented similarly 3, 4, 5, 6, 7, 8, 9, 10. So that's a full string. There's a divider after 3, there's another divider after 6 ones, there's another divider after 9 ones. Okay. So this picture now represents the solution 3, 3, 3, 1. Let's take our other example, 0, 5, 0, 5. That's yet another solution to this equation. Now how would that be represented? So 0 means the following, that the first divider occurs right in the beginning of this list. So the number of ones to the left of the first divider is a 0. Now I need a 5, so 1, 2, 3, 4, 5 ones later I have another divider. Now the next is a 0, which means that the third divider is placed at the same place more or less as the second divider. Okay. So this picture now, which has these 10 ones with 3 dividers placed in these positions, the first divider right in the beginning and the second and third dividers placed at sort of between the 5th and the 6th ones. This picture encodes the solution 0, 5, 0, 5. Okay. So now, so sort of from these examples, I hope it's clear that one can actually encode, so each solution to that equation, so each solution x, y, z, w to the equation x plus y plus z plus w equals 10. Each such solution can be encoded. So what we are doing is we are coming up with an encoding. We want to think of the same thing in a different way, which will be easier to count. It's encoded by the following thing. It's encoded by a string, so a sequence of, well, it's a string of what? Well, of 13 symbols. Okay, so what are these 13 symbols? Well, 10 of these symbols are just ones, so 10 ones. Let me write it as 10 ones, and there are 3 dividers. So 3 of these lines. Okay, so there are 3 dividers. Okay, so often instead of the divider itself, which is sort of hard to write often, when the other symbol is a 1. So to sort of make it uniform, we replace the divider by a 0. Okay. So we could as well say, instead of looking at a string of 1s and dividers, you might as well just look at it as a string of 1s and 0s. So for instance, so let me do it here. This string that we wrote out in the end, which had a divider in the beginning and so on, would be the following. It would be a 0 followed by 5 1s followed by 2 dividers, which means 2 zeros followed by 5 more 1s. So this string now of 13 symbols, 10 1s and 3 zeros, encodes the solution 0 5 0 5, okay, to that original equation. So we might as well just think of it like that. It's a string of 13 symbols with 10 1s and 3 dividers. So instead of dividers being this red line here, I will just think of the dividers as being written out as a 0. Okay. So now the question is, well, we wanted to count the number of solutions to this equation. It's the same as counting the number of strings of that form. Now this is something that we have already looked at. So this can be counted, the number of such strings. So recall when we, in one of the earlier lectures, we talked about writing out strings of A's and B's. We said the number of strings of length n which contain r A's and n minus r B's is just n choose r, because you just have to find the positions where the A's occur. Now this is similar. We have a string of 13 symbols and you pretty much only need to choose the positions where the, let's say, either the 1s occur, the 10 1s occur, or the 3 zeros occur. So the number of such strings is nothing but 13 choose 3, for instance, or 13 choose 10, which are of course both the same. Okay, so that's a solution to the problem. So now of course it's clear what the general solution will look like. So let's write out a general version of problem 2. So let me say, here's general version of problem 2. Find the number of solutions of, well, of what? Here I only have 4 variables, x, y, z and w. In general I could assume there are n variables. So the left hand side, let me replace it by n variables. Find the number of solutions of the equation. Let's call the variables as p's, p1 plus p2 plus, so there are n variables, p1, p through pn, and the right hand side here was the number 10. In general I could assume it's some non-negative integer d. Okay. So what's the assumption? Let n be at least 1, so there's at least one variable on the left hand side. Let d be some non-negative integer, and the question is, find the number of solutions of the equation p1 plus p2 plus p3 till pn equals d, where all the pi's are required to be non-negative integers. So where the variables are required to be non-negative integers. And again the solution methodology is the same. What we will want to do is to encode every such solution as a string of zeros and ones. So the answer now is the number of solutions to this equation is the same as, so this number is the same as the number of strings of, well, what's the total length of a string? So observe again, I need to have d ones, there should be a string of d ones, and the number of dividers should be n minus 1, because it's 1 less than the number of variables that you have, right? You only have, if you have n minus 1 dividers, it divides the string of ones into n parts. Those are the n values of the variables. So the number of strings of length, what's the total length? D is the number of ones and n minus 1 is the number of zeros. So total length is, which contain with d ones and n minus 1 zeros. So these are the dividers. Okay. So, this list of strings really counts the number of solutions to this equation, and of course we know now that this is nothing but d plus n minus 1 choose d, or if you wish d plus n minus 1 choose n minus 1. Okay. So, that completely solves the problem. So, of course the same thing can be phrased as, you know, in terms of balls. For instance, there are balls of n colors and you have a very large number of balls of each color, and this problem is just another way of saying in how many different ways can I pick d balls from such a box. Now let us sort of look at another problem, going back to something that we have talked about right in the beginning. So recall we talked about polynomials in more than one variable, right, and there we posed a counting problem. So we had the following question, we wanted to do the following. Suppose there are n variables, let us call the n variables x1, x2, xn. So these are the variables. So we are looking at polynomials in n variables, and what we want to do is the following thing. We said we in fact gave it a name even, let us call this number a d comma n. So we defined for each d positive a number called a d n, which was defined to be the number of monomials. So this is the number of monomials of degree d. Okay, in these n variables, of course. Now, and we sort of looked at some patterns, we wrote down the first few values of d, we obtained a recurrence relation for d, and so on. Now recall what is a monomial. A monomial is something of the following form, it is x1 raised to some number, x2 power something, and so on till xn raised to something. And so let us call these exponents as something, let us call it x1 power p1, x2 power p2, xn power pn. So what does a typical monomial look like? So that is a monomial where what are the pi's, with pi's being non-negative integers, okay, for all I, and what is the degree of such a monomial? The degree of this monomial is just the sum of all the powers. Right. So the problem that we looked at earlier of trying to count the number of monomials of degree d translates into the following: find the number of solutions to the equation p1 plus p2 plus p3 till pn equals d, where all the pi's have to be non-negative integers. Okay. So observe that is exactly the problem that we we talked about, that is the general problem 2. So from the discussion so far, here is what we conclude, that this number a d n that we studied a while ago is just the same as, well, what is it, the d plus n minus 1 choose d, because a d n is just nothing but the number of solutions. So a d n, as I said, is the number of solutions to the equation p1 plus p2 plus pn equals d, where the pi's are restricted to be non-negative integers. Okay. So observe that we have solved exactly this problem that was posed some time ago. So what I would like you to do is to go back to that lecture where we tabulated the values of a d n and where we obtained that nice recurrence relation and so on, and check that this in fact does match. So check, so here is a nice exercise to do, check that this in fact matches the values in the table, this matches our table from before, from one of the past lectures. Okay. So a problem on counting monomials turns out to be just a problem of doing some combinations with repetitions being allowed. Okay. So next time we will talk about something more on permutations.